All right, good afternoon. Wanted to take a few moments to go back to chapter 5 from our textbook and go over a little bit of the properties of gases. Now, for those of you who have listened to it before, we had some issues before with the previous video. Hopefully we can remedy that with this video. But starting off with basic properties of gases, going back to what we learned in our honors and general chem class about gases, we know that they are highly compressible, and they will take the shape of anything that you place them in, whether it's a balloon or a cup or a bottle or whatever it should be. They'll take that form. They're going to form homogeneous mixtures, and they take up about 0.1% of the volume of their container. So a very, very small fraction of the actual space available made to them. Now, how do we measure gas pressure? Well, pressure in all is the force acting on a certain area. In terms of what we're looking at here, we actually have the SI unit that we're going to utilize, which is called 1 Pascal, which is going to be 1 Newton per meter squared. Newton being our force unit and meter squared being our area. Our common unit, that we're going to utilize, 1 atmosphere, which you all should remember from last year, 760 millimeters mercury, which is also equal to 760 degrees Torr, and 101.3 kilopascals. I believe these are given to you on your sheet, but just in case you want to have them memorized, that this is an equality. So if you have to convert between them to make your calculations easier or to complete them, you should have these available to you. Now, how are we able to determine the actual pressure? One of the tools that we use is called a manometer. Many of you are looking at saying manometer. Now, what a manometer does is basically have a bulb or a container that has a gas. This gas is going to exert some sort of pressure due to its collisions. Now, on the other side in the tube, you have mercury provided, and also the other end is open, so that atmospheric pressure can have an effect on the gas. Depending on how far the gas pushes the mercury and the atmospheric pressure out, you'll be able to determine what your actual pressure is for that gas. A couple of relationships that become very important with this. If the pressure of the gas is less than that of atmospheric pressure, the way that you'll be able to find it is by taking the atmospheric pressure and subtracting the pressure from the mercury. If it's the other way around, though, if the pressure from the gas is higher than that of atmospheric pressure, then you'll add the two together. This will be able to be told by the distance, this H value that you have here on the manometer. We'll do a review of our gas laws. First one we're going to deal with is Boyle's. And this was an inverse relationship between the pressure and the volume. So as the pressure went up, the volume went down. And as the volume goes up, the pressure goes down, vice versa. Now, the other time that we're going to look at is Charles' law. Charles' law is looking at the relationship between temperature and volume at a constant pressure. And we're noticing again that as the temperature goes up, also the volume will increase as well. These are a couple of plots so you can see the relationship. We're also going to pay very, very close attention to what's happening in the relationship between Charles' law, because as you notice, there comes to a point where it seems like we run out of volume. That's going to come into play a little bit later, so you want to keep it in mind. Now, how do we come up with this absolute temperature scale? As you looked at the graph, you noticed that it stopped and we sort of ran out of volume at negative 273 degrees Celsius. Now, based on our law of conservation of matter, we know that this is not possible. But we're looking at it and seeing that this would be the point at which a gas would cease to move, or the molecules would cease to vibrate, if they did not condense into a liquid, of course. Now, this was discovered in 1848 by, as we know him, Lord Kelvin, who proposed the temperature scale based off of this. So, for our gas law equations, we're actually going to utilize the Kelvin scale, which are 0 degrees Celsius is going to be 273.15 degrees Kelvin. Absolute zero being the point where all molecules and things will stop moving. Now, back to our good old friend Avogadro. Now, Avogadro's main thing is he looked at the relationship between not only temperature, pressure, volume, but he also looked at how many moles of the gas are present. And his hypothesis or his thoughts were, if I have equal volumes of a gas at the same temperature and pressure, it'll also contain the same number of molecules, no matter which type of gas it is, no matter the mass of the gas. If I have these conditions, I should also have the same number of molecules. From this, we form what's now called Avogadro's law, saying that the volume of a gas at a given temperature and pressure is directly proportional to the number of moles of the gas. I.e., given the example, if I double the moles of gas in a balloon, I'll be able to double the volume of the balloon itself. And this is a diagram that's sort of explaining or showing you a little bit more of what's going on here. Paying attention to the volumes, the pressure, and the temperature. And though we do have the different masses, that we should also still have the same number of molecules present. Now, speaking of conditions that we're going to have to deal with throughout this unit, got to remember STP. STP standing again for standard temperature and pressure, where our standard temperature is 0 degrees Celsius or 273 Kelvin, and our standard pressure, 1 atmosphere or 760 millimeters mercury or 101.3 kilopascals. Now, combined gas law. Became very familiar with this last year, and we saw that as we would change one variable or the other, how it would affect the other parts. If we change the temperature, what would happen to the pressure, to the volume? And this is all still going to be based off of the same principles. So when we looked at Charles' law and at Boyle's law and Gay-Lussac's law, these are going to still have the same relationships, but now we're just taking all of the variables into account at the same time. Now, here we are with our ideal gas equation, or our ideal gas law. This is a situation where we'll start looking into when we come to our kinetic molecular theory, our KMT. But we want to see what are the conditions at which the gas will behave most ideally, meaning that it's not going to run or lose any energy, it's not going to have any issues with attraction or repulsion from other molecules. We want to see at what point is that going to be the best. Doing this, we come up and we utilize our R value, which is our gas constant at 0.08206 liters atmospheres divided by moles Kelvin. You want to make sure that you do have your units involved with each of your questions, because no units many times would be no points. Also, N standing for the number of moles of the gas. Make sure your units are present. Now, if you're looking at the information that you're given, and instead of atmospheres like we're used to, you're given pascals, you have to make sure that you can turn that 1 into kilopascals, but also notice that your R value also changes. So just be very mindful of your units. Now, these molecules are moving about at different speeds, at different velocities. And one way that we use to explain and to calculate this velocity is what's called the root mean square velocity. A formula is given to you here at the bottom of the screen. It's going to be the square root of 3 times R, where R is going to be our 8.3145 joules per Kelvin times moles, times the temperature in Kelvin, and then divided by the molar mass. Now, just a side note, you notice that your molar mass is in kilograms. It's not in regular grams. So you want to make sure that you can convert it back and forth as needed. Further applications, just knowing the relationship of this will help out a lot, as well as you're going to want to take note of the final formula that we utilize. Now, when we look at density in the beginning of the year, we noticed that the formula was going to be mass divided by volume. So we need to look at the relationship of what happens with the mass and volume over time. As the temperature goes up, we're going to notice that density goes down. If you think about the movement of the molecules, of the gas molecules, when you raise the temperature, they gain energy and they begin to move around a lot more. But as the pressure increases from the outside, the density also increases. So it's giving us a sort of a glimpse at what's going on there. Now, changing around our formula, we can actually solve and find the molar mass of a gas compound. You want to note this formula given here. The molar mass equals the density times R times T divided by the pressure. This equation is not given to you on the equation sheet, so you have to have it in mind. Make sure you study it, make sure you have it, just try to keep it as fresh as possible so that you'll be able to utilize it if the time comes. Now, Dalton's laws of partial pressure. Basically, our buddy Dalton, we remember him from our atomic theory, first developer of our atomic theory. He did a lot of experiments also with gases. And one of his main laws that we utilize today is that we have, in a mixture of any gases, however many gases it may be, each one of them exerts their own pressure. Now, when we add up that pressure, that tells us the total volume of the system. It tells us how much pressure is going to be there. So we can utilize a couple of things in our formula to calculate the total pressure. If we calculate them separately, we can always add it all up. Now, if we happen to collect any gas over water, we have to make sure that the vapor pressure of the water is also taken into account, just so that we can find what the actual dry gas or the single gas that we're trying to collect, the pressure would be, as was shown to us by the diagram given below. Now, because of the fact that we have these partial pressures involved, we also have to have an idea of how they're related to the overall pressure. And what we call this is our mole fraction, which is usually given to us by chi, which looks like an X. Now, if you have the pressure of the initial gas, then we can figure out what the total pressure, or using the total pressure in the mole fraction, what the pressure is. I'm sorry, blanked there for a second. Or if we have the total pressure and the mole fraction, we can always multiply them together to find out the individual pressure for each of our molecules. The formula that we're going to use for this is N1 divided by Nt, which is the number of moles of our gas divided by the total moles of our system, of our reaction. Now, last thing to note on this video, you know that mole fraction is a dimensionless number, meaning you don't have to worry about having any units when you calculate the mole fraction. They would have just canceled out. So this is going to be the end of our first video. Let me know if there are any other ways that I can help you. Write any comments or any questions at the bottom. I'll be checking out to see if there are any other ways that I can assist you. Thank you very much. Have a great